Hello everybody, and welcome to my presentation on AWS VPC and Networking, an introduction. So I'll look back a little bit to my days before the cloud, starting from the top left, the kind of servers that I got used to managing, maintaining, and then moving down to the bottom left, seeing the kind of networking, the cabling, and the kind of things that I had to maintain and manage and set up. Then moving across to the bottom right, when I moved to the cloud, using AWS to create virtual private clouds, VPCs, and network things a lot differently. Made it a lot more flexible, a little bit easier to understand in most cases, and a lot more scalable, for me anyway. And then to the top right, putting my feet up and relaxing. So in terms of content and the agenda for the presentation, we'll take a little bit of time to think about things like EC2 instances, virtual Elastic servers, and how networking affects those. Think about running our virtual network, remembering that by setting up our VPC and understanding how it's done, we know that we have control. So our IP ranges, you can use an IP address for this, an IP address for that. We can have subnets. We can think about good security, high availability, and of course we can make it scriptable so that we can deploy it as infrastructure, as code. We'll look at setting up a VPC from a basic standpoint, regions and availability zones, subnets. We look at route tables, internet gateways, and security groups. We look at VPC peering, NAT gateways, VPC endpoints. So we'll get started setting up a VPC. 4 of the main kind of tasks that you start off with, generalized really to keep it quite simple, high level. You would set up an IP address range. You divide that into subnets. You'd add routing, for example, making it accessible from the internet. And you'd authorize traffic in and out of the VPC where required. Now, when you need to choose an IP address and an IP address range, it often helps to have some understanding of how the machines, the computers, see these IP addresses to help you calculate the ranges, how many IP addresses would be available, and so on. So just in case required, we're going to quickly look at some binary arithmetic and working out how we translate an IP address that we see, for example, 172.3.1.0.0/16, into binary that the machine would see. 10101100, and so on. So this is CIDR notation, classless inter-domain routing. So we look at the grid at the bottom of the page. We've got 4 rows here. Now the first and third row, in black underlined, these are the bits in the sequence. So from left to right we have the 8th bit, and then 7th, 6th, 5th, 4th, 3rd, 2nd, and 1st bit. And then the 2nd and 4th row in red, with no underline, these are helping us calculate how many bits we have in the sequence. So to make it a little bit easier, we go from left to right. We start at 128. Now you notice there's a 1. Now these bits can only be 1 or 0, on or off, similar to, for example, a light switch. It's either on or it's off. So this means that we have 128. So we keep that. We move to the next bit, 64, we have 0. So we don't count anything. Next bit, 32, we have 1 bit. So we add that to the 128 that we had earlier. Next, 16, that's nothing. 8, add that onto the number from earlier. 4 plus 1 plus 4, then 0 and 0. So 128 plus 32 plus 8 plus 4 gives us a total of 172, which, as you can see, is the first section of the cider range. Next set then. So now we already know, really, if we just look at the example, that this will make up 31, sorry. We should be able to see how it works. So if you notice going from right to left, you notice the numbers underlined actually double exactly every time. 1 to 2 to 4 to 8, 16, 32, 64, 128. So if we go through the example, the bottom line, we have 16 plus 8 plus 4 plus 2 plus 1, 31. Okay. And then, of course, we have the slash 16 at the end. Now, this may change. This is just for the example. But what this essentially means is that the top 16 bits stay steady, and the bottom 16 bits can vary. So, for example, all the IP addresses within this range would all start with 172.3.1, and then the rest would vary. Okay. Now, using slash 16, you may use slash 32, slash 20. They'll give you a different number of available IP addresses based on how many bits will vary and how many bits will stay the same. Now, this example, slash 16, gives us 65,536 addresses. That's loads of space. Lots of room to play with. Allows us to make some changes later if we need to, and so on. But 172 is just conventional. We may use 10.0.0.0, 192.168, or we may calculate very specific ranges, especially if we have multiple networks and we want to peer them, we want them to work together. We often need to try and prevent any overlap. So rather than having two networks with the same IP address range, we would have two networks with different ranges. So all of the IP addresses allocated to resources within those networks would be unique, and then the two networks could communicate effectively. Then, of course, once we have the network in place, we need to divide it. We create subnets. Now, moving back a little bit higher level again, in terms of AWS, they've divided their cloud estate, their infrastructure, into regions around the world. For example, London, Paris, North Virginia. A VPC is within one region. So a VPC could never go across multiple regions, because the infrastructure deployed for that VPC is within one region. Now that region is split into multiple availability zones, AZs. So for example, within Ireland, you may have 2 or 3 warehouses, each geographically separated, so that, for example, if you have resources running in one warehouse, if that is unavailable, another warehouse, another location, another availability zone would be available to use. This makes things highly available. Now, a subnet, which we'll come on to next, is in a specific availability zone. Subnet can only be in one availability zone, never across multiple. So, of course, it's good practice to create subnets in all of the available availability zones within the region you're working with, because that then means that you can have resources in all of those availability zones. For example, things like auto-scaling groups with EC2 instances, so that you can spread the load, spread the resources across those availability zones, and if anything happens to any of those, the other availability zones can pick up the load. So of course we need to be able to route traffic. So for example, making it accessible from the internet. We do this using route tables. The route tables contain rules for which packets go where. You could assign different route tables to different subnets. So for example, you create a subnet that for your purposes, will be the public subnet. And then the route tables in there allow traffic to go public in and out of the VPC. Whereas you may then also have a subnet that you call a private subnet, which only allows traffic to be routed using the route tables privately within the network. Now by default, VPC's traffic is routed locally, so you can only stay within the VPC. So if ever you go and create a VPC, you need to put the things in place so that you can have access to the internet. By default, there is no access to the outside world. It's only within the VPC. So to do that, we can use things like an internet gateway, which is, as it sounds, a gateway to the internet. So we would route traffic that is destined for 0.0.0/0. So that is the outside world. We would route that traffic to the internet gateway. Now, one of the things that comes up often in certification exams and other kind of tests is the idea of an internet gateway. An internet gateway is only an abstraction. Okay, so it's not a single point of failure. So therefore, you only need one internet gateway in a VPC. So just remember, one internet gateway in the VPC. We also work with security groups. So just as an example, an internet server may accept traffic from the outside world. Okay. Obviously, you'd set it on particular ports, for example, port 80 or 443. But the backend servers should only allow traffic from the web servers. So, for example, the security group on the backend servers would allow traffic coming from the security group that is on the web servers. So this helps us facilitate and make best use of the principle of least privilege. So we can allow resources to communicate as much as they need to, but nothing more. Another good practice is adding descriptions. So labeling your security groups and even your rules within the security group. So anyone that is debugging, maintaining, just finds a security group and wants to know what it does, you can add a description to that. So for example, you may have some temporary rules while you're debugging, and somebody sees it and they wonder why the security group has SSH access to somebody's home IP address. It's because they're trying to work it out, trying to work out a problem. If you had a description, maybe who it's for, what it's for, then that just helps the kind of communication and collaboration and so on. Now, also thinking beyond the internet, networking isn't just the internet. You might actually have subnets restricting internet access. For example, private networks. You may connect to other virtual private clouds using VPC peering. For example, if you have multiple accounts, or just separating resources. You may even connect to corporate or other external networks. So instead of just routing by security groups, you can put web servers into a subnet that have an internet gateway access. So this is what we would call a public subnet. But then the backend servers don't need that internet gateway access. They only need access to the traffic that comes from the web servers. So you put those in what we call a private subnet that doesn't have access to the internet. So you can't get into the backend servers from the outside world. So as well as the internet gateway, we also have NAT gateways. And that gateway would be set up in a public subnet with a public IP address. And that NAT gateway allows private resources to access the internet, but not the other way around, not without an internet gateway. So for example, you may have servers that need access to download the latest versions of software, packages, and so on. But we don't want somebody outside the network to be able to get into the server itself. Internal traffic is then routed to that NAT gateway, and then that traffic will appear on the internet as if it was coming from the public IP address of the NAT gateway. So for example, you may whitelist the NAT instances or NAT gateway's IP address for access from our VPC. So if you're using, for example, a third party, an external service, and they need to whitelist IP address, you can use that NAT gateway IP address and then use the resources within your VPC to access that external service. Now generally I found personally that NAT gateway is more flexible and more resilient than a NAT instance. So previously I've used just an EC2 instance with some NAT software on there and then routed traffic from the resources to that instance. The problem with that is if the instance became unavailable for whatever reason, then so did the traffic from the application. It can cause quite a lot of issues. But also NAT gateway, although it does cost a little bit more, is fully managed by AWS. So obviously that takes a lot of the burden away and generally is more resilient. It's a little bit easier to make those changes on the fly as well without affecting so much of the service that the NAT gateway provides. We may also work with both subnets and security groups. So another live example really is a Bastion host or a jump box. Our administrators may SSH into that jump box. Now that may be, hardened security, very locked down. For example, SSH only allowed from a known IP address. So you set the security group to say only this IP address can SSH in. Okay, now that would need to be in a public subnet so that we could access it. But then you may have private resources in a private subnet, and the security group says only allow SSH from the Bastion host security group. So that way I would need to SSH into the Bastion host and then SSH into private resources. So a little bit of a simplification, but a little bit of a kind of a good way I found putting it is a subnet is like a yes or a no. Security group gives you finer grained control. For example, setting up different rules, allowing traffic from certain ports to certain IP addresses, or you could allow all traffic, or just specific traffic like port 22 or port 80 from IP address ranges or security groups. So also then on to VPCs and the rest of AWS, how they work with some other services as well. So you may have domain name registered in Route 53. You have a DNS record, for example, rstudio.dev.peak.ai, that points to an internal IP address, which may be attached to an EC2 instance, as a basic example. Moving down to the bottom left, thinking about speed and security, there's another feature of VPC called VPC endpoints. So by default, when you use S3, even if you have private resources, the traffic goes out to the outside world and then back in to S3. Similar with DynamoDB and others. But if we use VPC endpoints, it allows us to connect to an endpoint within the AWS infrastructure, within the region, within the networks, so that instead of going out to the outside world and back in, it stays locked down, which is generally more secure and in many cases even faster. You can also add a policy on that VPC endpoint so that you can lock down, you can decide who has access, who and what has access based on conditions, very similar to IAM policies. Moving to the top right, thinking about high availability. You may have a load balancer that serves an API. That load balancer is registered with multiple availability zones, like EUS 1A, B, and C. And then that would allow you to have instances, EC2 instances or resources within each of those availability zones. And then the load balancer serves traffic to all of those. And if then, for example, EUS 1A becomes unavailable for some reason, things like the auto-scaling and the launch configuration can be used to automatically spin up a new instance in a healthy availability zone, like B or C. That way you can maintain the amount of servers serving the traffic without degradation of your service until EUS 1A is available again. And then connectivity, maybe even compliance. Previously, you could only peer VPCs from the same region to the same region. So EUS 1 to EUS 1. So you may have multiple VPCs in your account or multiple accounts. But now you can actually do inter-region peering. So for example, a VPC in US East 1 peered to a VPC in EUS 1.